Okay, so maybe I'll seed the discussion with some questions, and you can choose to answer that question or comment as you will. So, TAMP research has been going on for a while. There've been a lot of interesting results, and maybe some challenges uncovered. So, what do you think is needed or would be helpful to see wider adoption of TAMP?
Yeah, so I can get started. I mean, I think this kind of comes up quite a bit, I think, but there is a parallel that is being drawn, I think, to how easy it is for students to pip install PyTorch and get started doing something with machine learning. Same thing, how easily accessible things like LLM models are. I think the same is not true with a lot of the, let's say, the skill learning pipelines or traditional motion planning or grounding and things like this. So I think that there is a real lack of software support for actually getting the robot to do the types of dexterous skills or even just normal skills. And I think that there is a real opportunity for good software engineering to be able to provide more flexible and expressive interfaces there.
Well, I'm not really a TAMP person, so but I imagine if I was, then one of the things I'd find difficult would be getting really good models to do your planning with. So I think TAMP is probably very nicely suited for relatively for tasks where there's a centimeter or two of tolerance, so pick and place kind of thing, where it's like place the apple in the bowl and open the cupboard and then put the bowl in the cupboard or something like that. But for dexterous tasks, contact-rich tasks, you would need a really, really good model to be able to solve that using planning. And it's very difficult to get that model, particularly from partial observations. So if you're just doing this in the real world with an image observation, converting that into a model that you can then do planning with is really difficult. So that's not necessarily the simulation issue. That's more like, how do you infer models of things from just an image of that thing? There's a lot of uncertainty there. But maybe the solution is you use planning for the higher level stuff and you use more kind of policy learning for the lower level things. So that's one way that you might combine them.
I'm trying to add a new answer that has not already been spoken for. I think I've come to the conclusion TAMP as a problem setting is not that you don't need. It's just that TAMP by itself, at least the current solvers we need, requires subcomponents, let's say motion planning or skills or perception. So the reasoning component is still required, but everything else, none of them are what you would call pip install ready. So if motion planning is not pip install ready, using TAMP, like most people don't even get to the point of interesting reasoning problems. What would usually happen is either you would just not have interesting skills to work with the reasoning system. So you're still sort of struggling at the low level. Or if you have a pick and place working somehow robustly, then many times the problem at the planning level is not very complicated that you need complex planning. You just like create a state machine and you'd be done. So a lot of this sort of is a dichotomy. The planning problem or domain will become much more richer as our systems at the low level, let's say skill-based systems, would become interesting. And I'm actually betting on this fact that as we have these skill foundation models which just work, we will have a lot more interesting reasoning problems to work with.
Yeah, just to add on that point, like it's quite familiar for me that one of my PhD students, I'll look at a demo that they show me, and there's something weird going on with the arm and it's sort of jerky, and there are some parts of that which don't look quite right. And I say to them, oh, you should probably fix that. And they just say, well, I don't really know how to. It's not what I do. And I don't know, this is what I have. This is how the crank arm comes, or this is what I have access to. But if there was like pip install, and all you got to do is run one line, which is like execute this end effective velocity, and it will do everything else for you, that would be awesome. And maybe it exists. Maybe somebody needs to tell me so that I can tell them. But it sounds like it doesn't exist.
No, I think that's a really good point. I mean, I think if anyone's, like you said, tried to gone through the effort of building something that you could call a TAMP solver or something like that, like, there's horror stories in every aspect of the problem. I mean, even if I think there was pip installable motion or something, then you run against like, what abstraction am I using in between things? How am I grounding everything? I don't know if there's any good universal answers for those problems. I think that's I guess one of the challenges of this whole problem is that it's really problem dependent or really setting dependent. I don't know. I don't know like how much universal. I mean, maybe this is why language is so nice, is that you can just talk to it and then don't have to worry too much about the internal modeling. But I really do think that's a huge challenge with this entire space.
Let me try to ask maybe a controversy-provoking question. So is TAMP the right problem to be solving? Or is it the right perspective on robotics? Could it be task and motion planning or just the and? Let's try the reverse order now.
Maybe I will give a controversial answer here. So I've only studied optimization. And task and motion planning, the and part has been very important because the argument, at least when I was a student 10 years ago, used to be the and is very important. You cannot solve these things independently. And my argument is, while that is broadly true, in general, you can get very far without the and. That's one. It's like arguing that a general purpose search problem is of a certain type of complexity. Yes, yet we solve search real time, live on your phone all the time. Okay? So it is very likely that there is a lot of value in thinking about problems where we can use learning or other solutions where it's not necessarily solving the joint problem. And it's okay to give up some optimality on that. But for speed and let's say flexibility, and then on a case by case is solve the and problem. Maybe that is what the community has not focused on, and perhaps because solving the discrete and continuous optimization problem is a fundamental optimization challenge beyond just robotics, and there is no good solution, at least that's what I know. So I think relaxing the problem assumption might be useful.
Yeah, I think similarly. I mean, it definitely makes sense that there's sort of some hierarchy here, and you're not just using the same optimizer or policy for all the different levels of that hierarchy. So we're seeing that coming into VLAs now, where there's a sort of a higher level, low frequency component outputting a representation which the higher frequency, more sort of dexterous component then conditions on. So that seems to make sense. But maybe, I don't know, in the human brain, maybe that's not a two-stage thing. Maybe there's some kind of, there's multiple layers of hierarchy or even something more continuous. But it definitely makes sense to me that, we should be, the task and motion planning should have different solvers. But it might be that there's many layers in between them, and, object poses, some of the work I was presenting about object poses, I think about that as sort of task planning. Where should those objects go? But that whole thing is within a broader task planning of like, should I be even tidying this table now rather than that table, or should I even go into this room, or should I even go into that house? There's all these layers of planning there, and each one probably needs a different optimizer. So I think it makes sense to, as a concept, task and motion planning. It's just like maybe not just task and motion, maybe some other words to fit in there as well.
I would say you kind of stole my point there. That I was going to say it's like task and motion planning and Dungeons and Dragons and so on and so forth. But no, I mean, I think this is there in the search community. There's like a huge amount of work on layered search, right? Like, you have something that solves the simpler problem, that solves the more refined problem, that solves the more refined problem for the heuristics or whatever purpose. I completely agree with that. And I guess trying to interpret Neil's question a little differently, I think like different problem domains need different guarantees from their search processes, right? Like, I don't know, the symbiotics domain, it seems like, you have this massive, you need industrial precision and all these kinds of things, right? That's a little bit different than tabletop domains where you're trying to, cook a meal or something like this. And I think that there are different needs and different types of optimizers or search methods or, policies that apply to all these different domains. And I think that there needs to be more thought in how you're layering things together. It doesn't need to just be task and motion. It can be scheduling. It can be, control. It can be all these different things. It's all just layered components working together.
We do already have more layers than just task and motion planning. So when, once you've solved the motion planning problem, there's something below that, and that's often running on the robot. We as researchers don't need to solve that because it's often a simpler problem, but it's still a problem that somebody had to solve at some point. How do you convert a joint velocity into the joint torques and maintain stability? So there's kind of at least 3 layers already there, and for some reason that lower level layer seems to be the easier one, and we don't really work on it as much. Yeah. But I think some people, like, probably a lot of my PhD students and, even part of my mind thinks, motion planning, that's solved, right? You should be able to get a robot from here to here and avoid that obstacle. Isn't that, did we solve that in the 90s or something? But like, it's not been solved. But it feels like it should have been solved because it seems like a problem where you just do some, classic optimization and, with a fully observable scene, it should be easy to do. And, but yeah, it's obviously not, that's obviously not the case.
I guess maybe one follow-on comment here is I think, if you're working in TAMP or adjacent problems, right, is like if you've thought really about the assumptions you're making between each layer, right? Have you thought about like what your controller actually needs? Have you thought about like what the planner actually needs? Because this is, I think, where a lot of things break down, is that you start pushing these, like I said, you start pushing traditional geometric planning with maybe kind of a crappy perception system outside of its comfort zone, and then things start really breaking down.
Yeah, I have maybe one question. Other communities are much heavier focused on benchmarks. The classical task and motion planning community does have strong benchmarks, right? And I think that's where you were alluding to, that whether we have the right benchmarks. So I'm kind of curious. I'm pretty sure that we don't. But my question is really, can we use newer technologies like LLMs now to build better benchmarks to be more general in what we actually want to solve, right? So it's kind of like a meta question of like, do we need a benchmark for a benchmark to then actually solve general planning or not? The other question is also like, of course, from the symbolic side, what we would do is we would just build our own benchmark and then put it out into the community and then it's solved for us. So it's great. But maybe next year we have something slightly different and it's not going to work anymore, right? So that's kind of what I'm trying to get at. So I would be interested in hearing your thoughts.
If I can interject, so our workshop in 2019 was benchmarking and exhibition of task and motion planners. And we did have a set of benchmarks, and some people tested their planners on the benchmarks. And other people's hair stood straight up when they thought, oh no, to publish, I have to solve these exact benchmarks. That's not what I want to be doing. Because if you have a set of benchmarks, it can end up dictating the direction that research community takes. But for better or worse, maybe that's what we want, or maybe we want to be more of it. But I will let the panel say what they think about this.
So I think benchmarks work really well when there's a clear metric as to whether something is good or bad. So ImageNet, for example, worked pretty well because it was like, okay, well, recognizing what's in an image is clearly very useful and it's a well-defined problem. It's binary classification, successful or not successful. Robotics has always been much harder because it's hard for people to sort of really define what a task is and what a success for that task is. So sort of in the robot learning community, it's been really, really difficult to come up with benchmarks because there were just so many tasks out there that robots could solve. But it feels like in something like maybe not task planning, but maybe motion planning is a narrower and more well-defined field where you could, it seems suitable for benchmarks, and you could just create, 100 scenes, and you've got to get from A to B and avoid the obstacle, and solve that without colliding as quick as possible. That seems a very if you solve that, then that seems like something that could be a good solution for that could be applied to lots and lots of different tasks. But the task planning part, yeah, I don't know, that seems a bit harder to find a benchmark for.
I mean, like, let's say for pure task planning, like pure AI planning, like ICAPS has been doing a lot of the planning competitions for years, and they have insanely hard PDDL problems and things like that really capture a lot of complexities of the search space. But I mean, the thing that I was saying is I don't think that's necessarily useful for robotics, right? We don't necessarily need to solve some weird abstract chemistry composition domain with our AI solvers. We need to, solve whatever the task at hand. And I think the point that you made earlier about can we even clearly define, like, a set of benchmarks for something like a task and motion planning problem that people broadly agree is a decent way of modeling the problem. I think even right now, if you go up to probably all the posters outside, everyone's saying they're doing TAMP, but everyone's making very different assumptions about how they're solving the problem, what things they care about, so on and so forth. I think that, yeah, for maybe something like motion planning, yeah, there are benchmarks that exist, but for something like TAMP, I think like we still need to even agree upon the language, the metrics, and how we even describe our tasks and problems. I think we're not even there yet.
I think if we can't agree on the problem we are solving as a group, then we have problems. I think of the many subfields within robotics, task and motion planning was one of the more structured. For better or worse, from efforts from a lot of people, TMKit has existed for a very long time. Like, I think there have been I think TMKit needs an upgrade, mostly because it was done in an era where simulators were very simple. So if you look at like the current planning benchmarks, such as TMKit, the complexity is usually mostly in either the geometry of motion planning or in let's say the task part. Usually the skills part are simplified because that is the thing that worked at the time when TMKit was created. Simulators have come a long way. As a community in robotics, we can solve many low-level things much better. Like we can turn knobs, turn switches, that stuff. Like 10 years ago, this was not a thing. You could grab blocks. That was about it. Like and because of that piece, I believe we can create much more interesting task environment. Now that said, how should we build such an environment? According to me, we should learn something from what I would call, there is a community in machine learning, and particularly RL, called open-ended. So the whole idea is defining a particular RL environment is not sufficient because we don't know what the environment is going to be. Might be a better idea to learn. So instead of designing a particular benchmark, of course, we'll need to seed the framework. We might want to design what I would call, not necessarily, the word is not meta benchmark. The word would probably be the utility tools to create new environments. Arguing that we cannot do this or my problem is too broad, I think I do not accept that as a valid argument. Language people do this all the time and they're fairly ambiguous. What is a benchmark for math problem? They still have one. What is the benchmark for reasoning? They still have one. It may not be complete. It's fine. We'll have 10 of them. So I think as a particular concrete idea, we should first of all focus on average case rather than the worst case. We can have certain worst case, like, oh, there's a particularly hard problem we know from a planning domain, and maybe it will not work. But I think we should create average case. Average cases can be mined from use cases, whether it's from industry or home or wherever. In fact, I have actually done this exercise. You show current OpenAI models or any sort of LLM, VLMs, an image or a scene, and they are actually very good at generating problems. Like, here's the scene, what can I do? And they create task plan problems very, very well. And then converting them into executable plans would allow us to create what you would call statistically correct task and motion planning problem. So we can definitely do that, and if we do that in simulation, as a community, we'll go very far.
Okay, so I think to respect our speakers' time constraints, we'll have to conclude there. So thanks again to our panelists. So I want to thank all of you for participating in the workshop, all of our speakers today, all of our poster presenters, and Clayton and Ty this morning, and Bill on the other end of that Zoom call, who've been managing the AV, and will hopefully be uploading a recording of the workshop talks. So I hope this workshop has been interesting to everyone. I hope there will be some continuing and fruitful discussions, and thank you all.